Hello, welcome everybody. Good afternoon. Thank you for coming to our talk, Don't Let Secrets Get Away, How to Monitor GitHub for Secret Leakage. My name is Jordan Wright. I work on the labs team at Duo Security. Just last year, we were acquired by Cisco, so we are Duo Security, now part of Cisco.
My name is Nick Mooney. I'm also an R&D engineer on the labs team.
And my name is McNiece, and I'm a data engineer at Cisco and working on my PhD at NC State.
Sure. Can you hear me okay in the back now? Is that good? A little bit more? Yeah, awesome. Okay, so what we're going to cover today is we're going to talk about secret leakage on GitHub. Now, I know a lot of us here are practitioners, so we're familiar with the general problem that we don't want to commit secrets, right? So we're going to skip over those basics, and we're going to approach the problem from 3 different angles. All right, what I like about this conference is it allows us to be a little bit scientific, a little bit empirical, and to be practical. And those are the kind of things that we're going to try to do today. So the first is that we're going to give kind of a behind-the-scenes look on what happens whenever a secret is committed to GitHub. How do we get the headlines that you see in the news every so often? Then we're going to show you the results of a large-scale, kind of first-of-its-kind study where we try to answer the question, how bad is this problem really? Can we study this on a large scale and measure the problem across all of GitHub? And finally, we're going to give kind of a taxonomy on methods that organizations can take back and use to try to detect and monitor for secrets being committed to GitHub for their own organizations, depending on a number of different parameters, depending on a number of how much control you have and kind of what your situation and environment looks like. So before we get started, we need to kind of set a baseline to make sure we're all talking about the same thing. And the first is defining what a secret is. A secret means like 10 things to 5 different people. So for the purpose of this talk, we're defining a secret as a hard-coded value that, when compromised, can result in unauthorized access. This means that we're not talking about sensitive information that maybe you just don't want other people to know, code that wasn't meant to be committed, intellectual property. We're specifically focused on those hard-coded values, examples being SSH keys, passwords, or API keys. Okay? So with that background in mind, let's talk about what happens whenever, as a developer, I'm working day to day, and it's time for me to spin up some new AWS resources. I gather the AWS credentials, put them into the code, which maybe let's just say it's for testing, and then I commit them upstream. This is usually what we see happen. These headlines are from a number of different places, news articles, postings on various social media forums, and the headlines all look the same. Secret was accidentally committed up to GitHub, and all of a sudden I get a huge bill for all these compute resources that I didn't mean to spin up. Okay? And you'll notice the dates are highlighted. This isn't something that we just saw a brief spike in and then it went away. This is a problem that we're seeing across multiple years. Even today, this is something that people run into, which is why we're here talking about it at ACOD. Behind the scenes, the flow looks something like this. I'm the developer. I commit my secret upstream, where GitHub receives that, and then 2 things happen. The first is that GitHub publishes it to a global event stream. This is an API that we're going to talk about a little bit more in just a few minutes that anyone can access. Okay? The second thing that happens is they index it in a global code search. So you have the ability to go and search through different values, and this could come back and have some negative effects, again, that we'll see in just a moment. But on the back end, the attacker is looking for these 2 sources of information. On one hand, they could be using the code search to look for secrets exactly like the one that I just committed, or they could hook into this global event stream and try to monitor commits on a very large scale, looking for a very specific value. And either way, they end up with the secret. They then use that and in an automated fashion start to spin up compute resources. They can do something like crypto mining. They can do something like sending out phishing emails, you name it, using those resources, and I'm left paying the bill. So these are the 2 methods that we've talked about earlier. The first is code search. So back in 2013, GitHub introduced the ability for you to search across any number of projects for particular values. This is really useful for me in my day job whenever I'm prototyping with new libraries that maybe I haven't used before. I need to figure out how are people actually using this thing. But it has some side effects too. People quickly realized that if I search for, let's say, the beginning of an RSA private key, I can get back results for private RSA keys. This had some pretty big effects, but it also has some limitations. The first limitation, of course, is that I can only search for hard-coded values. I can't search for more complex things like regular expressions. And we'll talk about what that means whenever we're trying to study this at a large scale very shortly. So code search is one angle, and the other angle is the Events API. GitHub offers an Events API where you can hook into their stream of anything that happens to, let's say, a repository, a user, an organization, or even the global GitHub public commit stream. All of these are sent and pushed down to you as a JSON object that you can then iterate through, traverse through, and get more information. So this is one way that attackers can monitor GitHub over time, or likewise, organizations can monitor for their own information that we'll see what that looks like in just a minute. So at this point, from a labs angle, from an R&D angle, we thought about this and we said, it'd be really, really cool if we could try to measure this problem. All of us have seen these headlines. We've seen these case studies. It's happened to me personally on a side project before. So I'm very familiar with the outcome, but how often does it actually happen? No one's really investigated this at an empirical, large-scale study. So we should look into this. And so imagine my surprise and joy whenever I see that a paper came out that did this exact same study, and they happened to work at our company. So that was really exciting. And at this point, I want to turn it over to Matt McNiece to talk about the results of that large-scale study.
Awesome, thank you. So we started this study called How Bad Can It Get? Trying to figure out how bad this problem is, how bad this problem is on GitHub. And so everything I'm going to talk about for the next couple minutes is available in this paper. If you Google it, it should pop right up, and it has more detail than I'll go into as well here. So in this study, what we did is we did the first large-scale longitudinal measurement of secret leakage on GitHub, looking across billions of files and about 6 months of data. We developed 2 new approaches to reliably detect secrets at scale and in near real time, and we showed that from this data set that secret leakage is pervasive and constant and affects developers of all capabilities. So like Jordan mentioned before, a lot of the existing work is pretty much this, of opening up GitHub, typing in begin RSA private key, and getting some results back. Like a lot of those articles that he mentioned, this is exactly what they did. The problem, though, is that if you kind of see in the second result here, which is kind of hard to see, probably, it says replace with your own key file, which obviously isn't a secret. And if I just reported back and said, oh, there's 2.5 million things that say begin RSA private key, there's 2.5 million keys on GitHub, that doesn't work. Because it gets that scalability, but it misses that accuracy piece that we really wanted to look at. And so in this next couple minutes, I'm going to talk through 2 key challenges that we addressed. The first is how do we know when we found a valid secret versus a random key or a test string? And second, how do we do these at scale? So to get into that first challenge of what is a secret. So from this list, at least one of these is a secret. Can we figure out which one it is? So going through, it's probably not this first one because it says example key. And it's not something that's sensitive. The second one doesn't look like an example key, but it's the same character of 1, 2, 3, 4, 5, A, B, C, D, E over and over again. And so we're going to say that that's not random enough. This third one looks random. I don't see any repeated patterns to it, but it's a UUID or a GUID, which appear all over software and aren't necessarily sensitive. From these last 3, they all look random. There's no repeated patterns, but you can kind of cheat and tell you that the second one there is actually the secret. And while any of those could have been a secret, that second one is the only one we have good confidence in. Because the key looks like it's random, and we found out that all Google API keys have this unique signature of AIZA followed by 35 characters from that character set. And the probability of us finding that string randomly by chance is minuscule, so we're calling that generally acceptable error. And these unique-looking keys actually appear all over super popular APIs on the internet, right? Places like Google, Facebook, AWS, Twitter, Stripe, all have API secrets with a identifiable pattern to them. And so the first thing we did as part of this paper was go sign up for hundreds of different accounts on these sites and generate a bunch of tokens and make sure they actually are all always the same, and they are for these 15 different APIs. So the second challenge we looked at was how to do this at scale. And so we kind of took two different approaches to it. The first is to use the GitHub search API that Jordan talked about earlier, and the second was to use a snapshot of all the publicly licensed repos that's in Google BigQuery, if you've looked at that before. And generally what we did is we downloaded a bunch of candidate files from both of these sources and ran regexes and other, some tooling on them. They do both kind of give us different perspectives into the problem of secrets on GitHub, though. With the search API, we can look through the most recent commits, and so you kind of get that near real time, and we showed that you can get 99% of all public commits in real time within GitHub's rate limits and be able to see everything. On the BigQuery side, it kind of gives us a more historical perspective. So we took one snapshot and saw however many repos were in there. I have that on the next slide. So what did we find? So we ran the search API for 6 months to continuously scan and pull down files, and we took a BigQuery snapshot from April 2018, and of that, there's billions of files in that corpus. We pulled about 4.3 million offline to do more detailed analysis on, and from that, we found 200,000 totally unique valid secrets. Importantly, we found a median new number of 1,793 secrets per day showing up. So this is happening all the time, constantly. So what did we find? So the most common secret we found were Google API keys, which isn't terribly surprising. They have a ton of APIs that are useful to developers in other cases. We also found a bunch of asymmetric private keys, which again, all sorts of uses. Then we kind of got into, so what, right? I leak my API key, what's the worst thing that can happen? So we kind of thought of it, there's data integrity violations, right? If you have your API keys out there, somebody can read or change your data without you knowing it. Privacy violations too, if you have somebody's calendar API key, you can find out where they are, what they're doing, and things that somebody might not want you to know about. You can also lead to message abuse. You could send email or tweets or texts to somebody else to create, phishing campaigns or whatnot. And some of these can also lead to direct monetary loss. Like Jordan was saying, you could take somebody's AWS keys, spin up some Bitcoin miners. You could take their Stripe keys and send yourself money. There's big impacts to these things. So the next thing we wanted to dig into is, do users realize when they're committing secrets? And so what we did is we took some of the secrets that we detected and kept looking back at their repos and their files and those secrets for the next 2 weeks to say, do these ever go away? And so on the left, this is kind of the short-term view. So it's number of hours after detection, and the right is number of days after detection. And we kind of see this initial drop-off in the first couple hours of a user deleting the secret or deleting the file that the key showed up in. But it flattens off after a couple of days. There's still about 82% of these secrets that are still there, possibly today. We also noticed that more secrets or files are removed in the repository because of the nature of how Git and GitHub cache stuff and Git history works. A lot of times if the repo is still public and they haven't completely scrubbed their Git history, you could still go find these secrets. So some of these API tokens or these APIs actually have multiple parts to them. So for example, with Twitter, they have both an access token and an access token secret. I think AWS has this too, the access key and your access key ID. And the purpose of this, right, is that you have to have both of them to be able to authenticate or use the service. However, we found that oftentimes one of them or the other would have that distinct pattern we could reliably look for. And so what we looked at is, well, if I know where the one that looks distinct is, can I find the other one? And we found that in almost all cases, when one of those secrets is leaked, the other one's leaked too. So this as a mitigation technique for vendors to say you have to have multiple parts of your key isn't great, because oftentimes developers will just commit them both anyway. Highlights there. So I've been talking generally about some numbers. Let's look at some specific examples of leakage. So we found about 2,000 personal RSA keys that looked like they were being used for SSH. So you could take these, connect up to their boxes as that person, and do whatever. We found about 2,000 or 1,800 OpenVPN config files that had RSA keys in them as well. 13% of these did not have password authentication on it either, so you could connect up to VPN endpoints. We found 54 secrets in gitignore files. That's not what gitignore is for. And we found a single user that had about 564 Google API keys. We kind of dug into that one a little more, and it looked like they were using that to rehost YouTube videos on their own website and potentially serving some malicious content as well. And finally, we found an AWS key for a major government agency in a Western European country. So that was an interesting one. And so when we were looking at this, we kind of kept asking ourselves the question, why is this happening? And a common hypothesis is it's developer inexperience. And so what we looked across were developer experience, like how old their account is, how many contributions they have, repo maturity, and repo activity, or like active repos or whatnot. And between all of those variables, we found no statistical significant difference between those and leakage. It can happen to everyone in every type of project, regardless of your experience. In fact, on that previous slide, the AWS key for the major government agency was leaked. We found his profile and then their LinkedIn. And they claim to be a senior with 10 years of experience. It could happen to anybody. It could happen to you. So how can this problem be mitigated? Essentially, once a secret's committed to public GitHub, it's gone. The only thing you can do reliably is revoke it. And we think GitHub's in a really unique position to mitigate this. In fact, after we concluded our research in October of 2018, GitHub announced that they began scanning public code commits for some secrets and working with providers to get those secrets revoked, which is awesome. Some of the known providers I have up there, I think they've added some more since then, including Duo, perhaps. And so if you leak a secret, the only thing you can do is revoke it. And so with that, I'm going to hand it off to Nick, who's going to talk a little bit about how, as an organization, you can detect and prevent this.
All right, thanks, Matt. So I'd like to talk a little bit about how organizations can both prevent this from happening and detect it happening based on essentially how much control they have over their environment. So on one level, or sort of on one side of this axis, maybe you control all your developer machines. They're tightly locked down. You can push whatever code you want to them. On the other end of that scale, maybe you're just a volunteer working on a globally distributed open source project, and you don't have that kind of fine-grained control of the development experience. Some of the things you might think about sort of controlling are the development environment, the developer machines, source repositories, CI pipelines, and your level of access to all these things really determines what your capabilities are. First, though, if you want to just study historical GitHub data, if you're interested in replicating some of the research that we've done here, I just want to point out that there are several options available to you. I think there's a lot more to discover here. GHTorrent and GHArchive both provide downloadable snapshots for offline processing, if you'd like to do that. And then both of those services, as well as GitHub themselves, also provide Google BigQuery data sets that allow you to make real-time queries against historical data. So the first situation you might be in is where you control the environment fully. You're able to push code to your developer machines. And in this case, you want to look into hooks. Hooks are scripts that run at various points in the Git workflow. And hooks can be either on the sort of local developer machine or up in the receiving server. A pre-commit hook, in particular, checks for sensitive information before allowing a commit to proceed. So this would happen actually on the developer machines. The issue here, or not issue, but sort of limitation here, is that hooks are not actually committed to the repository. They are stored separately in Git configuration. So if you'd like to deploy hooks to your developers to make sure that secret scanning tools are run and secrets are not able to be committed to the repository, you need to push that out separately from actually just syncing that repository. We also have pre-receive hooks. These are something that you can use if you have server-side support. So if your repositories are just on GitHub, this is not an option to you. But if you're using GitHub Enterprise, GitLab, if you control the actual server that's receiving these commits from your developers, you can do that same kind of scanning server-side and reject commits that contain secrets. How you respond to this really depends on your threat model. But at the point that, in terms of a pre-commit hook, you may be okay with the risk that a developer accidentally tried to commit a secret, but it was only local to their machine and never made it to the repository, you may not revoke that secret. At the time that the developer attempts to push to the actual server that's hosting your repository, that might be a different story. If you don't control the development environment fully, but you do control the repository or the GitHub organization that you're hosting your code in, you can look into GitHub webhooks. Webhooks are triggered on various events. And in particular, you can wire these up to trigger secret scanning tools every time, say, a commit is pushed to a repository that you control. This is powerful, and I also just want to point out, kind of along the lines of the last bit of that last slide, if you use webhooks to trigger secret scanning tools, you're only going to be able to discover secrets after they've been committed to your repository. Right? So in this case, as Matt kind of discovered, it's very, very, very difficult to roll that back. So at the time that something's actually been committed to the repository, you've triggered that hook. If a secret is found, revocation is a much more reasonable approach. Additionally, if you're a service provider wanting to keep your customers safe, like Matt said, GitHub actually provides some support for doing this. You can submit regular expressions that match against your API tokens and other secrets, and GitHub will actually scan in real time new commits and will send you, the service provider, the operator of the service, a webhook when a token matching your regular expressions are found. GitHub delays the global event feed, like the public event feed, by 5 minutes, and this is almost certainly to give service providers time to react before the sort of general attacker public is able to do that. I think this is a really good sell for if you're a service provider constructing your tokens in such a way that they are easily regexable, or even with known prefixes. If you're in this position, it's important to think about what the proper response is going to be. AWS is an example that I like here. They had to balance, so say AWS receives a webhook and one of their tokens has been detected in a GitHub repository. Revoking that token may cost their customers a lot of money, maybe very unreasonable for them. Right? So AWS implements a notification approach, doesn't automatically revoke access even when tokens are discovered publicly. If you're running a service that's less real-time or has less customer impact, maybe in that way, revocation could be an option. I also just talked a bit about hooks, and I just want to show this great diagram that Matt created showing where in the Git flow these different tools live. Right, so over here on the left, we have the developer and pre-commit hooks run locally on their machine, right, before they commit to their local repo. We have pre-receive hooks that can run, and this says github.com, but really those are running, custom Git pre-receive hooks are running on infrastructure you control, but determine whether or not the server hosting the repository is going to accept that commit. And in the case of github.com, both attackers and your security team are able to access those events and search APIs. Separately from that, you can have your own organization infrastructure, and GitHub can send you webhooks, and you can do secret scanning sort of off to the side. If you don't control the repository, and you don't control the developer machines, you can't use hooks, you can't use any of these methods we've discussed so far, but you can use the GitHub events and search API. I'm going to talk a little bit about both of those. The search API works great when you have secrets that have common prefixes, so like those Google API keys we saw. There's no way to search for, say, just high entropy strings. That's something that some of these secret scanning tools do. But if you have an easily sort of discoverable prefix for your secrets, this is very possible. Median time to discovery per Matt's research via the search API is about 20 seconds. But the range on that data was half a second to 4 minutes. Right, so again, this is a common thread, but the assumption here you need to make is that if you've used a public API to detect a secret, an attacker either has or has had the ability to, and you need to treat that information as public. The events API is interesting and is usable in cases where you're searching for less scoped data. If you're searching for just arbitrary sort of high entropy strings, if you don't have a common prefix, you can use the events API. It's a fire hose of data. It's pretty much in real time, minus that 5-minute delay. And you can scope it to an organization, repository, or a user, or you can actually use it to access all events continuously across GitHub. We attempted to determine how feasible this was going to be, and we ended up with this nice little graph. What you're seeing here is the result of us grabbing the first page from the Events API, basically with the list of all events across GitHub, waiting the minimum time that GitHub asks you to wait between API requests, and then grabbing the last page, and seeing basically if that window of events that we have access to has slid all the way off. What you're seeing here in color coding is the probability that you will miss at least one event if you obey the GitHub guidelines on API usage. So as you can see, there are some times of the week, some times of the day where you could feasibly get access to the list of all GitHub events, but particularly in the middle of the week, that becomes infeasible. If you're in one of those positions where you may not have control, or actually even if you do, we've developed a little bit of open source tooling to allow you to wire some of this stuff together, and Jordan is going to talk about it.
Okay, so the last scenario that Nick described was one in which, as an organization, I don't have much control over the repositories, the developer machines, and this may seem kind of exotic. Like, wouldn't an organization have that level of control? But not always. You can imagine a case where in a large enterprise, there's tons of developers, there's tons of sub-organizations, there's tons of repositories, and it's not really feasible for me to try to enforce something like pre-commit hooks, for example, whenever you can't even commit those to the repository. So this scenario is actually fairly common, and we found that it's a little bit underserved. And so what we did was we built a tool that can kind of help fill that gap, giving that level of monitoring for that particular scenario. So the way it works is that it brings in information from two different sources. The first is through event polling. Now, Nick brought up a really great point, which is it's not really feasible to monitor the GitHub event stream and collect every single public event, because we respect the request from GitHub, which is to rate limit ourselves. And so you may ask, well, how do attackers do this, right? How do they bypass this request from GitHub? And this is going to come as a shock. They ignore it. They don't listen to it, and they just do what they want. And then, you know, I have no doubt that behind the scenes, GitHub is actively working to throttle those. But in the same way, that's how places like GitHub Archive and GHTorrent, those offline mirrors, that's how they work. Is it seems like they've been given some kind of, like, you know, they're doing it for a good purpose, kind of an agreement where they can poll at a higher frequency to make sure they get an accurate mirror of all of GitHub. But for us, just an average organization, we want to make sure that we respect the request from GitHub in the way that we monitor events. So to that, we have a couple of options. Maybe we can't monitor every single event, but we can monitor repositories that we know about. We can monitor developers that we know work at our company. We can monitor organizations that are underneath our company. Even if we don't have the ability to influence the settings on that organization, we can at least passively monitor the activity of that organization to watch for secrets being uploaded. So by filtering our scope using that Events API, we can get an accurate collection of events and not hit that missed sliding window that we saw a little bit earlier. So that's one source of information, and as an added bonus, if you do have the ability to set up webhooks for a project, we have the ability to ingest those as well. As we get new events, we send them to what we call detectors. Now, we didn't want to reinvent the wheel here. What Secret Bridge is not is a tool that can look at a repository and tell you, does it have a secret or not? Those tools exist. There's tons of them. And the way they work is they typically have a regex-based approach with an optional, just look for high entropy strings that have been in the latest commit, right? So instead, we're going to let them do the hard work. We have the ability to plug in your own detector. We have built-in support for the detect secrets and get secrets tools, since those are pretty popular, well-known secret detection tools. And then we get the findings from that tool. We say, did you find any secrets in the latest commit? If they did, we can notify you. Because half the battle in our line of work is being notified in the right way, or we can start taking action on some of these things, right? So to that end, we have Slack support, we have Teams support, and we have just dumping out to a console where you can send it to a SIM and do whatever you'd like. These are just a few of those features written up in a bulleted way as opposed to a diagram. And you can find the URL to the GitHub repo here. And one thing that I want to point out, which I think is, it was a low lift, but I think it's a nice value add, is that we have a markdown file in that repo called tools.md. And what we did was, as we were doing the research, we just dumped in links to every secret detection tool we could find. The idea is that this gives you a great baseline to start from if you're an organization looking to bring this kind of capability into your CI pipeline, into your monitoring infrastructure. The question is, where do I start? What tools are out there? What can they do? And which one's right for me, right? So that's what tools.md is. We just keep a collection there. If you find any that we haven't seen before, we'd love to get a pull request from you. So wrapping up, I want to hit on a few points that were mentioned throughout the talk. First off, 1,700 secrets a day. Holy crap, right? Like, that's wild. This shows that this problem isn't gone. You know, this is still something that we're battling today as a larger industry. And as Matt mentioned, it can happen to absolutely anyone. It's such an incredibly innocent, simple mistake to make, but it can have significant impact. That's why it's important as us as practitioners to be able to measure first, then monitor, and then take action, right? That's kind of the motto of how we do our day-to-day work. And there are things that we can do based on our level of control which can allow us to have that ability to do that detection. And if you're in the room and you're a service provider, you're actively issuing API keys to customers and you want to work to protect those, a quick addendum, we don't have that full support for Duo yet. That's something we're looking into. And we recommend every service provider in this room look into that as well. It's a service that GitHub offers, and it's a way for you to get awareness if your customers are accidentally sending up API tokens that you've issued so that you can take the right action for them. Nick mentioned that it's always a balance. You may not want to revoke right away. Maybe you want to put them in an increased monitoring kind of scenario, right? Depending on what's right for your risk levels. So these techniques are out there. We have a blog post that I'll link in the Slack channel where we give this full taxonomy of all these different methods. And last but certainly not least, we've open sourced Secret Bridge to make this even easier. And before we go, I have a quick demo that I wanted to show everyone, if that's okay. How do I get to Firefox here? I've learned over time I'm scared to touch anyone else's computer except for my own because it would break immediately. So shortly as we were wrapping up this research and we were getting ready to publish our blog post, Secret Bridge, we saw another link that caught our attention. A researcher, I'm not sure their identity. Is there a way to maximize that? That'd be great. Excellent. That caught our eye, and what they did was they built their own secret detection tool that they call SHH Git. It's like, Git kind of thing. I can. Let me see if I can zoom in a little bit. Yeah, I'll have to do that. There we go. Let's do something like this, right? Is that a little bit better? Awesome. So a little bit more, sure. I'll do it. Oh, nope, it's too far. Too far. But this is the best we can do. It's the best we can do. Technology limitations. So what they've done is they've built their own secret detection tools that work based on the event API. So very similar to the approach we've talked about today, right? Where you pull the events API, you watch and monitor those commits, and you look for a set of regexes that they've programmed into their solution here. And then they've shown that through a web interface. I'm a huge fan of this because it's very visual and it allows you to see the impact of this problem. And doing a quick scan, I'm not gonna add all these up. I see, let's call it close to 150, 160-ish secrets, and not scrolling down. So I mean, there's even more below, right? That's since we've been talking. So in the background, you see the stream being refreshed as people are adding new secrets. You can see these live. So if you ever need just a demo of seeing this in action and seeing all of the metrics that we've talked about, the measurements that we've talked about in a live way, I love this webpage for that. So I'd encourage you to go take a look. Again, we'll paste all these links in Slack. And at this point, I think we're ready to answer any questions. Thank you. Is it this one? So I'm going to go to thank you slide.
First off, Matt, that was an awesome paper.
Yeah, thanks.
I was working on detection cases out of that for about 6 months. It's incredible. A couple of things I found on the client side. There are other ways of instrumenting things by hooking file system syscalls, looking for writes and file creates. for paths that match, Git repos and then scanning there. So even if you can't enforce a client-side pre-commit hook or pre-push or whatever, one of the other like config level hooks, you can use file system audits and scan it with Yara and OS Query. OS Query lets you fire off a Yara scan. The other thing I noticed is that the storage for commits in the commit history on local repos, on checkouts, on developer checkouts and things like that can become all garbled with lots of things like unreachable commits, and the status of the file system that you see doesn't map to the actual file structure of what's visible. There can be things like people trying to erase Git history or something like that, but you've still got diffs stored in the storage. And some of those things aren't reachable by walking through the Git repository history itself. They're unreachable commits. It's what Git cleans up when you run git fsck. So there's interesting things there if you find checkouts on local systems. So I sent you a DM with some other things. I'll touch base. Thank you.
Yeah, and to that point, if there's ever any kind of like supplemental reading resources you have on that stuff, I'd love to read them if you wouldn't mind posting them in Slack. That'd be great.
Sure, I sent a copy.
Great, thank you.
Other questions? Oh, sorry.
I wanted to share on the attacker side, like I'm sure you have seen data, but based on what you said, this is actually a real problem. We have helped a few organizations that had an incident because of this, and there was not just one attacker, but in a few minutes they had like 3 attackers in their network using those API keys. So it's something that it's not only they're leaking secrets, but actually attackers are actively monitoring for this and automating the whole process, right? Because it was like 60 seconds. Like there was an incident that within 60 seconds there was a new EC2 instance running, mining Bitcoin. So it's obviously there is some automation behind that.
And you're absolutely right. It's one of those examples, and maybe this is just me. It kind of feels like we're getting to a point where we have to fight the automation with more automation, right? Because our window of detection is shrinking, and we talked about just using the search API. The events API has a 5-minute delay where ideally if you're doing token scanning, part of that you may have some time to respond, but just through the search API, the median time to discovery was 20 seconds? 20 seconds, right? And that's not even enough time for me to Google how to undo a commit, right? So you're right. We have to start building on these solutions. And the good news is people like GitHub are taking a leading position in this place, right? With offerings like token scanning, where they're saying we're willing to work with organizations to kind of tackle this together because it's a problem that affects a lot of people. It's a really hard one to solve because you have to automate it from end to end. But even then, I agree with you completely. There's definitely room to grow. Did anyone want to?
Awesome talk. One question that I had is, did you guys run into any issues with GitHub's event API rate limiting? Did that hinder any of this research at all? And did you have to circumvent that, or did you work with GitHub, or how did that work?
Yeah, so the research that we did with the events API was really to determine whether or not it was possible to grab all of the public events. So we really didn't run into the kind of usage that would actually trigger rate limits. My personal understanding is that what GitHub asks of developers is significantly more than what they will actually rate limit against. I chatted a little bit with some folks from GitHub about this, and basically, at this point, their documentation, if you read it, the wording is that it's kind of a nice request rather than a strict rule. But yeah, during our research, we didn't actually run into the kind of usage that would have triggered rate limiting.
I can add to that as well. And so when we used the search API instead of the events API, and we showed, I think we have a paragraph on it in the paper, that we got 99% coverage with the trigger phrases we were using with just one API key and have some tests showing that that's possible. So if you have a more restricted scope for what you're looking for that you could like search for with trigger phrases, you can get 99% coverage with one key.
Anybody else?
Thank y'all.
All right, thank you guys. Cedric, are you out there? All right, we're going to start up the next one in just a second, so stick around.